Hello, everyone, and welcome. My goal with this session is to help you with your text mining and natural language processing projects using the free open source Spark NLP library. So let's get started. For those of you who don't know it, I'll introduce the library and also give some updates about what changed in the last year. Then we'll talk a bit about new improvements in features, in accuracy, in speed and scalability. Then show you some code so you can see just how easy it is to either use existing stuff or train your own models, and we'll walk through some examples. So Spark NLP, for those of you who do not know it, is the most widely used natural language processing library in the enterprise for 3 years in a row, based on several industry surveys, the largest one being led every year by O'Reilly Media. And basically what we see is that there are great libraries that are used a lot in research, in academia, but when people move to commercialize and productize text mining efforts, they often move to Spark NLP or scale with Spark NLP at that point. As a company, Johnson Labs is focused on the healthcare and life science space, and specifically within healthcare, based on the latest NLP industry survey, Spark NLP used by 54% of teams. Also, with the same survey, Spark NLP is also used by 36% of all teams that use any NLP library. And the last thing to note, and really this is a thank you, to the community overall, we've seen a 16x growth in the number of downloads of Spark NLP just from January 2020 to April of 2021. So it's kind of 16x in exactly 16 months, and just announced crossing the 5 million downloads milestone last week. So Spark NLP is an open source software library for state-of-the-art natural language processing, with the goal of taking the latest improvements in research mostly around deep learning and transfer learning nowadays, and providing you with production-grade, scalable, and trainable versions of those new innovations. The library has a full APIs for Python, which is the most widely used, as well as Scala and Java, which are heavily used as well. It also comes with an ecosystem of pre-trained models and pipelines, and we'll show you where it is online. Right now, there are over 1,400 of them, with more being added every week. The library is well known for being very actively developed. So we've been releasing software every 2 weeks since October 2017 until today, and intend to continue doing it going forward. And once again, I would like to thank the community, the industry, for helping out, providing feedback, code, documentation, bug fixes, examples to help it. This has enabled us to not just keep releasing, really keep growing functionality in a very significant way, and keeping up with a very fast-moving field in terms of actually giving you state-of-the-art accuracy, speed, scalability, which kept improving every year. So one thing that happens if you claim that you're doing state-of-the-art, it means that you're almost always re-implementing things you've done before, because by the time you implement something, a new paper comes out, there's a better way to do something, which then we go and support. As I mentioned, basically every industry report that you look at would have Spark NLP as the most widely used library. There are definitely other excellent ones. There's Spacey, there's Hugging Face, there's NLPK, Stanford NLP, which are used in different contexts. Some of them have been there longer. Some of them are really better suited for research and academic. Spark NLP is really best in place where you need a production-grade NLP pipeline and NLP library, whether working on your own machine or being able to to scale to large-scale systems. And as you can see here, from the largest companies in the world to companies in retail, in energy, in healthcare, in pharma, in insurance, have been using the library for quite a while now. We're 3.5 years in, and have been helping build it and helping grow the community around. Our focus is usually not on providing new implementations and new results, although there are several papers where we've written new academic papers. We've actually advanced the state of the art. But usually our focus is on taking new academic results and productizing them. Because as I'm sure you know, if you've tried it, there's a very big difference between having an academic paper that says, yes, we've been able to improve accuracy or do something new, and something that you can actually use day to day and depend upon to do your job and have systems that work and serve people and do good. And you can see some of the aspects that we focus on as, first of all, trainable and tunable systems. So all the models and all the capabilities I'm going to show you today with Spark NLP are trainable models. So if you need your own name entity recognizer, your own document classifier, your own emotion detector, your own spell checker, your own language detector, all of those are trainable and tunable. Another important thing is privacy. So Spark NLP we do not do anything as a service. This is designed to run on your infrastructure within your environment. It does not send anything outside. It does not call home, does not share anything with any third party, not us, not anyone else. And it's heavily used in high compliance industries, so healthcare, finance, life science, insurance, government. Explainability and reproducibility is obviously important. The results and the accuracy metrics I'll show you here are reproducible in the sense that you can take the notebooks, you can run them yourself and see the same results. And there's been a lot of work around logging, experiment tracking, giving you better visibility into what your experiments are doing. We've done work on hardware optimization. I'll talk more about that, but making sure that out of the box, you make the most of the hardware you have. Of course, that Spark NLP in terms of scalability is based on Apache Spark. And until today, it's the only open source library that's natively scalable to really to any clusters, CPUs, GPUs. And the last thing is really building a community, which of course, Data Plus AI Summit is a big part of. And then, there's also the NLP Summit, which we organize as well, to help educate, share lessons learned, case studies, and help grow the community. In terms of what it does, Spark NLP is really an end-to-end library, meaning that you really shouldn't, and usually you don't use any other libraries in conjunction. It starts with the basic and simple functionality, kind of the things that NLP and Spacey and Jensen do. So you get tokenization, lemmatization, stemming, part-of-speech tagging, dependency parsing, normalization, data extraction, sentiment analysis. On top of which, you get the more sophisticated deep learning models. So state-of-the-art name entity recognition, information extraction, document classification, emotion analysis, and we'll see some examples of that down the road. The library comes with its own transformers, and there's a fairly large ecosystem of them. And what it means that we take care of optimizing how we load transformers, how we cache them in memory, if we need to, how we distribute them across the cluster. We actually have some custom implementations to profile and optimize speed and memory use, and make sure that you can easily share transformers across different parts of the pipeline. So if you have, for example, multiple entities you need to extract and then multiple document classifiers, you can cache and share the same embeddings, both for training and for inference. Another advantage of just having a single pipeline does everything from your basic sentence segmentation to question answering, translation, summarization, is that we can then natively scale the entire pipeline. So you're not to the point where you want to scale to a cluster, but because you're mixing in, you're doing some things with Spacey, some with Sanford, some with Hugging Face. Really, not everything benefits from scaling, or we need to reload things or move things between memory spaces multiple times. So here, both in terms of speed and also just as importantly, in terms of just elegance of the code. So just you write less code, it's more elegant, it's easier to understand, easier to debug, and really what we are seeing is that really outside kind of homework examples, when you get to real systems, very often the feedback that we get from people is that Spark NLP takes some time to learn the API. But then at the end, what people see is really that the resulting system is much simpler than what they thought they'd have or what they had before. A month ago, we've introduced a new major version, which is Spark NLP 3. Spark NLP 3, first of all, now runs on Spark 3, on Spark 3.0 and 3.1. We also maintain support for Spark 2.3 and 2.4 because there's a lot of enterprise use in production of the software. So we are committed to that and committed to make sure that wherever people use Spark NLP in production, it's gonna run and run well. Spark NLP 3, if you look at the compute platform we support, so now we support really all Databricks versions, 6x, 7x, and 8x, whether with CPU or with GPU, and we've tested and optimized on all of them. If you're working on a single machine, and this is very common, sometimes you get the question of whether Spark NLP only applies if you're working on a cluster, but probably most people just work on their local machines. So you have builds for Linux, for Mac, and for Windows that all work. You can work either just on a local machine, or you can work within Docker, with or without Kubernetes. We have support for the latest AWS EMR versions. We've tested on AWS, on Azure, on GCP, Hadoop, both the 2.7 and 3x versions, in Cloudera or on your own builds. And so as you can imagine, we spent a lot of the last quarter testing this on different environments and making sure, not just that it works, but also that it's highly optimized. And what you can see here on the right are recent performance benchmarks. These are benchmarks we actually did on Databricks 7.2, on AWS with 10 different machines, just comparing Spark NLP 2.7 with Spark NLP 3. And as you can see, calculating BERT is between 6.5 to 7.9 times faster. So very, very significant boost whenever you're using BERT embeddings. And for the most common use case of name entity recognition, we see a 3x speed up on GPUs, but really just between the two versions of Spark NLP. So it just goes to show the significant amount of profiling, optimization, and also work with both of Intel and Nvidia that we've done in the last few months. The next thing we're going to talk about is accuracy and what the state-of-the-art accuracy mean within our context. But before that, I'd like to move and show you some examples of the library in action. To reach this website, basically all you need to do is Google Spark NLP, and the first site that would come up is this page, which is nlp.johnsonlab.com, which is the homepage for the open source library. What you can do here is, of course, you can get started and get download instructions for Python, for Java, for Databricks, for Scala, for AWS, whatever your environment is. You can look at some demos, or you can, of course, go to the code itself if you're looking to contribute. Interesting tabs that you have here. There's the entire documentation, the entire reference documentation for the library. There's a learning hub, which has a whole bunch of videos and articles about the library. There is the models hub, and as we mentioned, there's a big collection of models. There's, as of today, 1,444 models exactly that are here, and all searchable by task, by human language, and by Spark NLP edition. And there are live demos. And the live demos are interesting because they're not just demos, you also have the code examples to go with them. And as you can see, for each demo here, you have the live demo. So for example, if you go to identifying fake news, you have a string lit up, which shows, okay, is Donald Trump a KGB spy? Maybe, maybe not. We have the actual text. The model ran on it, and in this case, the model predicts that this is a fake news item with a confidence of 100%. Right? If we look at the different examples, so Rubio, Neb's key former Romney aide, you have the text here, and in this case, the model predicts that this is real, that this is not fake, also with a confidence of 100%. So this is just one example of document classification. Document classification is the text example where you take a piece of text, right? In this case, this text, and you need to classify it, right? In this case, we're only classifying whether it's real or fake, right? You do the same thing, for example, with spam detection. What's important to know is that for each of those string demos, you also can click open in column here on the left, And this would give you the actual code behind this notebook. Okay, so what you have here is over 100 examples, over 100 Colab notebooks. So you can click open in Colab and you can just run it yourself. If you want to change the text, run it on your own text, just open in Colab. This is now your own private environment. You can change the parameters, change the model, change the demo text, do whatever it is that you need to do to see if this works for your own case. And then you can see the code. So one thing, in terms of installation, installation is a one-liner now. Okay, so you just do wget on setup.noslab.com/colab.sh and run it as a bash script, and that does whatever it needs to do to install Spark NLP in a Colab environment. Then you have a set of imports, and then another one-liner just to start the Spark NLP session. And this is important because one useful thing to know about Spark NLP is that, and you'll see it in the code here, is that you really don't need to know the Spark API, or you're not forced to use it. If you're just trying to do something local on your own machine, and you say, listen, can I just use pandas on a local machine, and I don't need cluster, I don't need all of that. Really, you do not have to. If you want to, Spark NLP.start return the Spark session, right? And you can configure it. You can configure multiple nodes, large cluster, Databricks, whatever you need to take advantage of. In this case, what you can see here, you can see some of the examples: KGB spy, President Barack Obama. And then what we do, we define the main code defines the NLP pipeline. So Spark NLP is based on Spark ML. So an NLP pipeline is a Spark ML pipeline. So we use the same pipeline class from Spark ML, which makes it super easy to integrate Spark NLP with the rest of your Spark workflow, right? So if you need to load 100 terabytes of text data from S3, you just load it into a Spark data frame, right? If you need to, after NLP, you have some ML tasks that you want to do with Spark ML. Not only you can do them, and it's going to run distributed on the cluster. So it integrates very nicely with the ecosystem. And really, the more complex your use case, the more you'll see the benefits in terms of optimization. And what we're doing here for classification is very simple. We take the text, we create it into a document, and that's a Spark NLP document. That's kind of the first column we create. We calculate sentence embeddings. So we load universal sentence embeddings, the pre-trained model in English, and we ask them to calculate it. And then we actually call the document classifier. In this case, we load the pre-trained model. And here the model name comes from the string lita, from the combo box, which in this case would be the fake news model that really comes out of the box. Then we define a pipeline where we call the document assembler, we calculate the universal sentence embeddings, and we classify. And that's the entire pipeline. Once we load the results, you can do two things with an NLP pipeline. You can do fit to train. So every pipeline is trainable. In this case, we do not need to train. Everything is pre-trained. So we just show it as an example. And then the other method other than fit is transform, which means please do inference. Okay, once you do inference, you see the results, and you can see that Donald Trump's KGB spy is fake. President Barack Obama said former Secretary of State Hillary Clinton use of that was real, and so on. You can see that really what the classifier did on your own data. So that's one example of a document classification. So back here, let's look at a different example. Another very common task is entity recognition. So entity recognition is the task of looking at a piece of text and identifying entities. So for example, William Henry Gates III was born this date, and he's an American business magnate, and so on. And you want your name entity recognizer. In this case, it trains specifically to identify things like person, organization, date, and a few other things. So you want to find that William Henry Gates III, all four tokens together are one entity, and that entity is the person, right? October 28th, 1955 is a date, right? And so on for the other entities. Here again, you have the examples, but just as you can click Live Demo, you can also click Colab Notebook and go to the notebook. As you can see, this notebook is super similar. You have the one-line installer. After the installer, you're going to have the imports. After the imports, you do Spark NLP.start. You have the example text here. You define the pipeline. Okay, so this pipeline creates a document. It tokenizes, meaning splitting the text into words, based on the model name. So if the model name is a name entity recognizer deep learning, it loads that model. If the model name is a deep learning with BERT, it loads a different model that is based on BERT embeddings. Then it loads so you load kind of the correct model name. And then the converter basically collects all the tokens into single long entities. So you can see the 4 words, one entity. You define the pipeline, you run it, you do transform. One other interesting thing to show here, there's another open source library that we've open source, which is Spark NLP _display, which enables you to see all the visualizations you see in the Streamlit apps within Jupyter. So once you load it, once you import the NER visualizer, it's NER visualizer.display, and then you can basically look at the results and see them here within a notebook, just as we've seen before, and visualize your NER results. And similarly, if we go back to nlp.com, go back to our demos, other interesting entities, you can look at things like emotion detection. Right, so we can look at this tweet, for example, and this is a surprise tweet. Okay, and we can look at another example. This is a sad tweet. My dad turned off my internet. The horrors. This is another surprise tweet. The moment when you see your friend in a commercial, cool. And this is a fearful tweet. Okay, and this is also an example of a multi-class document classifier. So you have those examples as well. One other thing I want to show before we go and talk about accuracy is spell checking. Another very useful thing that Spark NLP does out of the box is spell checking and spell correction. So you can see an example here, and just zooming in a bit. Apollo 11 was the space flight that landed the first humans on the moon. As you can see, that was like flight and first are automatically detected and corrected as wrong spelling. And same thing, if you go, you can open this in Colab. Same thing, installer imports the pipeline defined. And you can look in the example. So please allow me to introduce myself. I am a man of wealth and taste. Just about 10 spelling mistakes here. And you can see a visualization of the original versus the corrected version. Please allow me to introduce myself. I am a man of wealth and taste. And really the only mistake this does is here, correcting this to end. Everything else, about 8 or 9 mistakes are corrected correctly. One very important thing to know about this model, this model established new state of the art because it can use context. So it can correct the same, basically same mistaken word at different tokens based on the context of the words around. So with that, with those examples, this is basically how we use the library out of the box. And with that, let's talk a bit about accuracy and what it means in this context. The most important thing to know about the word state of the art is that it's not a marketing term. It's a real academic term. Claiming state of the art in anything means that you have a peer-reviewed paper on a public academic benchmark that others have validated and can reproduce. That shows that, for example, you have better accuracy than any other published paper on the same benchmark so far. And that is what we mean when we say that we claim to deliver state-of-the-art accuracy to you. What you see on the slides are 3 examples that are specifically in the medical space. And as I mentioned before, this is where the company focuses on clinical and biomedical NLP, where I would say that right now, if you go to Papers with Code, that tracks over 4,000 different leaderboards, and go to the medical name entity recognition category, you'll see the Johnson Labs and Spark NLP hold 8 of the 11 top places for the 11 leaderboards and benchmarks that are collected there. Some of them are, as you can see here on the left, are on biomedical NLP, so being able to extract things like chemicals, anatomical parts, gene products, and so forth. Some of them, like you can see on the right here, are more on the clinical side, so being able to extract clinical concepts, so diseases, drugs, or being able to correctly de-identify text. So de-identification is one of those tasks really only in the past 2 years we can finally do as accurately as humans, really, in an automated fashion, which is really changing that industry. For the open source library, really one of the most common use cases, if not the most common use case, is name entity recognition. And the most widely used benchmark is the Xeon CoreNLL 2003. Spark NLP prides itself on not just having a deep learning implementation, not just having a kind of state-of-the-art deep learning implementation, but actually having a lot of custom features and tricks within that implementations that enables this to really deliver the most accurate system for production system. Okay, I think there's one academic paper that does kind of 2/10 of F scores more, but that is an academic paper, meaning that the code is incomplete. It's not usable if you wanted to. If you wanted something that runs today, 5 lines of code, widely used in production that you can depend on, really with the options that are there, Spark NLP is the best option, and we have kept it that way by really re-implementing NER basically every year for the past 4 years as different implementations improve. And with us in general, our secret is that really we do not have one. So it's not that we have a specific algorithm or specific model that's slightly more accurate than others. It's really the fact that we release software every 2 weeks. Whenever a new paper comes out, we read it. If it is better, we try to reproduce it. If it does reproduce, we'll give you a production grade implementation as soon as possible. Another important thing is for you to get the best accuracy right out of the box. So for example, with NER, all the default parameters are really what you'd expect to get the optimal accuracy, which really makes it very easy to go and reproduce our results. And they're actually open source notebooks, and if you go to the Spark NLP workshop online, that would enable you to do exactly that. Another thing that's obviously important these days, if you want to achieve state-of-the-art accuracy, is transfer learning and the ability to reuse transformers and embeddings, so that you can basically apply transfer learning by using what the embeddings have already learned, and reduce the amount of custom annotated data or custom documents that you need to train your own models. Spark NLP includes really most of the models that have achieved state-of-the-art results in recent few years, and well over 100, if not hundreds, of different types of embeddings and transformers that come with the library and enable you to make different trade-offs. So as you know, some embeddings transformers are tuned for specific domains, right? Like the legal domain or the healthcare domain, or the trained for German or Bengali or Japanese. You should use those. There's also trade-offs between, for example, you look at BERT, right? There's BERT large and base and mini, and there are, I think, at least 24 different sizes of embeddings, right? And you have things like distilled BERT, right, and other basic condensed BERT that try to trade off memory and size versus accuracy, of course, in an optimal way. Other than NER, another task for which Spark NLP is today claims until, of course, until someone does better, and then the community progresses, is multi-class and multi-label text classification. So we saw one simple example of text classification, which is always, is this text fake news or real news? And you can do the same. Is this spam or not spam? Is this positive sentiment or negative sentiment? Multi-class classification refers to the case where there are more than 2 classes, basically. So you can say, oh, this is a news item. What kind of news item? Well, oh, maybe it's sports, maybe it's business, maybe it's technology, right? Maybe it's politics. And it could be 1 out of 4, 1 out of 50, 1 out of 100. By default, the trainable multi-class classifier within Spark NLP, the deep learning one, supports 200 classes. The other thing that's interesting about this classifier is also multi-label, meaning that you don't have to choose only one label for the class of document. And you can see an example here. One of the pre-trained multi-label deep learning classifiers that come are toxic content detection. And as you can see in the top right, and I'm not going to read those out loud, but one sentence can be an identity attack, as well as an insult, as well as an obscenity, as well as a threat, right? As well as being sexually explicit, right? So of course, you could all think of sentences that where more than one label would apply, right? And if you want to find toxic content and also know what you're dealing with, you're looking for something that's not only multi-class but also multi-label, right? And would explain, for example, the confidence levels for each label. So that comes pre-trained with Spark NLP, but of course you can also train your own multi-class, multi-label, multilingual classifiers using whichever kind of either word embedding or sentence embedding that best fits your use case. Here are some of the ones that come out of the box. So the document classifier deep learning, the multi-classifier deep learning, the sentiment analysis deep learning are all trainable models. They can all use all of this variety of both word and sentence embeddings, meaning that you have really a lot of choice from really simple models that need to run on a smartphone and have to, or even run on the browser, right, and have to really optimize how much memory they take, right? So in some use case, it becomes, look, we need a 10 megabyte sentence embedding model. In other cases, really, you just want to make sure you optimize accuracy at all costs, like clinical use cases, and then it's fine. Look, if you need to hold a 5 gigabyte embedding model in memory, that's no problem. So we support all cases. Another state-of-the-art model that comes out of the box is a language classifier. The language detector DL can recognize, comes with different pre-trained models. The largest one being able to detect 375 different languages. Smaller ones can do, I think, 175, 180, 20, 60. So it really depends on what your use case is. These models are small. They're around 3 to 5 megabytes, meaning they load very quickly into memory and they work very, very quickly. And depending on the language, the accuracy we are seeing is between 97 and 99% accuracy. And the only caveat that text needs to be longer than 140 characters, right? Because of course, if you have a single word like ciao, I mean that could be Italian, that could also be Romanian, right? And you'd always have these words that appear in multiple languages. If you have at least 140 characters, that's usually what you measure accuracy on, which is still fairly short. The context spell checker, as I mentioned, is able to look for specific patterns, and as the name suggests, look into context. On top of that, you can train your own spell checker, and people have done this for different languages or for specific business domains. You can also add custom dictionaries, right? So if you have things that only exist within your company, specific jargon like specific project names, product names, or just whatever slang you use, you can add this as custom patterns. And in general, one of the things that I don't talk about here is for each of those models, assume that you have quite a few features and configurations that are required in real-world use cases. And this is really part of having kind of an industry-ready system. One benchmark we have is the what's called the Holbrook benchmark. It's kind of really the main academic benchmark we found for evaluating spell checking, automated spell checking systems, and comparing to Gemspell, which is just another widely used Python library for spell checking. We make less than a third of the number of errors it has on the Holbrook benchmark. Accuracy aside, assuming you have something that works as accurate as it can, right? And of course, state of the art does not mean that it's always correct. It means that it's as correct, as accurate as we know how to do it today. The other super important thing that we care about is speed and accuracy. So those things have to work in real world systems. Today, one of the things that really take most of the time and the profiling effort in those systems are using embeddings and using large embeddings. So other than using kind of pre-trained transformers and optimizing them for GPUs, before trade-offs, one thing that we worked a lot on and released in Spark NLP 2.6, it's really just building a custom implementations of how we load transformers and how we use them, based on some really recent papers in this space around how to correctly implement dynamic shape and how to optimize memory. As you can see here, we are able to improve memory consumption by 30% and improve performance of just inference by 70%, just by smart loading and smart inference. So that's something you get out of the box with Spark NLP with kind of no other trade-offs. Another thing that you may want to do depending on use case is to be able to decide whether you want to use, BERT large or BERT based or BERT medium or BERT small or BERT tiny or BERT mini, and there are at least 24 of them out of the box, which basically provides some trade-off. The most accurate one would be large, but probably if you use if you use BERT tiny, depending on your use case, you may only use 1 or 2 percentage points of accuracy and have a model that is, for example, is 24 times faster and 28 times 28 times faster and 24 times smaller in terms of memory. So it may well be worth your while, right, to have a model that can reply in 8 milliseconds in terms of instead of 40 milliseconds, and takes 5 seconds to load into memory when you start your server instead of 2 minutes. So all of those options are yours, and as you saw, it's really just a configuration change as when you write your code. The other important thing that we do for you and the community in the industry is to work very, very closely with both Intel and Nvidia to make sure that we deliver optimized builds for both of these. So the graph you can see on the right is, this is an Intel kind of approved and reproduced benchmark on the Intel Xeon second generation scalable processors to make sure that we actually have customized build with MKLDA library and a specialized TensorFlow library that make use of the deep learning instructions on those chips. Similarly, with NVIDIA, we've just recently, especially with Spark NLP, they've done work to make Apache Spark GPU aware, and they've done quite a few optimizations on just data frames. So we've done some work with them on that, and also some work on really the kind of the core deep learning tasks and key building blocks to make sure we get the most out of that. And really the most important thing to know there is that we do all of that for you. We make sure that Spark NLP is really as optimized as it can be for whatever hardware you put in place. Other than speed, another big thing for Spark NLP is being able to scale. So there are 0 code changes that are required to scale a pipeline to any Spark cluster. As you saw in the code, when we define a pipeline, it's a Spark ML pipeline. And then that pipeline, it's really the same thing. First of all, it's serializable, but then it's also, it distributes to a cluster really with no code changes. Really where we benefit here from Spark itself is from all of the optimizations that are already exist within Spark around execution planning, caching, minimizing shuffling, minimizing serialization, optimizing serialization formats. So all of those very, very hard distributed computing problems are some of the things that Spark does really well. So really, we've just done the work with the open source ecosystem, with Databricks, to make sure we make the most of them and use them correctly and give you that benefit. You can see here on the right one example of really just scaling, and this is training your own NMT recognizer and seeing how things scale across the cluster. One thing to know, and you can see in the list of caveats, is that of course parallel computing is not magic, and the speed up you will get when you go to a cluster would heavily depend on the task. Right. So for example, if you're doing inference and the model is P3, then you can trivially parallelize inference across a cluster, and you're going to get near linear speed up. If you're doing things that are natively iterative, right, like for example, training a new RNN, that you're going to see sublinear speedups. And here are some examples of that. So this is a recent benchmark looking at the full data sets of Amazon reviews. So these are 15 million sentences, 255 million tokens. And you can see how they work. This is also on Databricks, on AWS with 10 fairly weak Dell servers. And you can see the speed up that we get going from a single node to 10 nodes just doing tokenization or also doing name entity recognition, right? So tokenization is a fairly simple task, right? Not deep learning based. So you actually see super linear scale up, right? You can see when we add 10 nodes, we get more than 10 times of the kind of number of words per second that we can process. With you NER, you do see speed up, but you see sublinear speed up, right? So we add 10 nodes, the number of words per second goes less than 10x. And this is really what you need to see, right? Because it's going to be very, very dependent on your specific pipeline or specific use case. This is another example on the same data set. This time looking specifically at calculating BERT. Although I would say this is also, these are, as you can see, these are fairly small machines in terms of memory, 32 gigabytes, but we are using multiple cores, and we are using definitely, of course, multiple machines, and letting Spark do all of the optimizations. So one thing though, if you have 1,000 machines, you definitely want to understand Apache Spark in detail to understand how to optimize its configuration. But usually, if you're dealing with 10, 20, 60 machines, you should expect very nice, just out of the box speedups. So we spoke about accuracy, we spoke about speed, we spoke about scalability. What I'd like to do now is take a few minutes to show you some code so you can evaluate for yourself how easy to use the library is for different use cases. And usually there are three types of uses. Either you just use a pre-trained pipeline, which means, look, I just want one line of code and kind of just do this thing as well as you can. I don't care. Sometimes you come and say, look, I do want to tune my own pipeline because I have my own language, or I need to use my own stop word removal, or my own stemmer, or I need to train my own document classifier. So I reuse some things and train some others. Or you may want to just train everything on your own. So as you saw, the key component in Spark NLP, the key abstraction is a pipeline. So we take the text and we take it through stages, right? So we split it into sentences, we split it into words, we remove stop words, we may lemmatize it, right? Then we calculate word embeddings, then maybe we train an MNT recognizer, right? Or we extract emotions and so on. And that's the basic abstraction. So the simplest thing you can do is that you can just reuse an existing pipeline. So let's look at the code here. In this code, what we want to do is we just want to run a pre-trained name entity recognition. So we import Spark NLP, we import the annotators, we import the pre-trained pipeline. We call Spark NLP.start, and this is really GPU equals to is all you need to ask for the GPU build and the GPU optimizations if you are running the GPU. The next thing we do, and that's really a one-liner, we load the pre-trained pipeline. So pipeline equals pre-trained pipeline explain document DL. So what this pipeline does is it takes a document, it splits it into sentences, it tokenizes, it does some basic text cleaning, and then it calculates embeddings, word embeddings. If it's DL, it calls, I believe this one uses glove out of the box, but there's also a document BERT if you want it to use BERT, and it runs name entity recognition. Okay, so it does all of that pipeline in one line. What this line does is kind of go load the pipeline, then load all the models this pipeline requires, load any embeddings or other configuration file that it requires, load them into memory, either locally, or if you need it, multi-core, if you need it to distribute across the cluster, it does all that. And then you have a ready pipeline. Then here you have the text, and the one-liner to actually annotate the text to get your results is a result equals pipeline.annotate on the text. And then you can see what your result is. Okay, the result object is always just a simple pipeline dictionary. Okay, so you can see the tokens, you can see the entities, right? You can see everything that the processing did, right? And in this case, you'll see that William Henry Gates, the third born, is an American, right? And it will actually find those tokens and show the type of each entity that was discovered. So this is really all you need to do. You start Spark, you load the pre-trained pipeline, and you call pipeline.annotate on the text that you're looking to go. There could be a case where you can say, okay, this is nice, but the problem with the pipeline is that I cannot really configure it. And if I want to change or add steps or reorder steps or for example, run multiple models, then I need to build my own. So here's how you do that. You import the library, and then you configure your pipeline. So the first stage is you create a document assembler. So you take the text to create a document. The next phase is you create a tokenizer. So from the document, you create a new column called token. And this is how it works in Spark ML. So we add columns to the data frame we work in, and each processing step populates one or more additional column. Right? This is, first of all, the Spark ML design principle. It also makes it really easy to parallelize inference, right? Because work on different columns or different documents can happen easily on different machines. In this case here, what we do, we do stop word removal. So we remove stop words. And so we create a new stop word cleaner. We call the .pretrained, and we just use here the stop word removal in English. So from the tokens, we get clean tokens. And we set it to be not case sensitive. This is, by the way, how you configure specific steps if you need to. Then we calculate BERT embeddings, and we calculate them on the tokens without stop words. Okay, on the clean tokens, we create an embeddings column, and then we load a pre-trained NRDL, so name entity recognizer deep learning model, NRDL BERT in English. We have the pipeline. Once we have a pipeline, you already know there are only two methods that matter: .fit to train your own, or .transform to actually apply context. So in this case, for example, this is how we add a stop word cleaner. Right, here's how we configure it. You can use your own tokenizer, your own sentence splitter, your own custom embeddings, whatever may need to be the case. The third thing you may want to do is decide to train your own models. Okay, which looks exactly the same. There are only two things that you need to change. You need to actually load the training data, and instead of calling .transform, you need to call .fit. So here, if you look at the code on the right, we do the imports, we start Spark NLP, we load the training data, and you can see we have a helper class called POS. In general, we have helper classes to load training data into data frames for all the types of training data sets that Spark NLP supports. So it's usually a one-liner if you have kind of a CSV or a kind of a classic training data file that you got online or you made yourself. And then the pipeline is we create a document, right? So we document assembler. We use a sentence detector, so we split the text into sentences. Then we tokenize it, so we split each sentence into words. And then here a POS tagger we train via perceptron approach, right? And we tell it, oh, the input columns are the sentence and the tokens, right? Because to detect part of speech, you need to know what word and what the word is, but of course the word within context. Right, because of course the same word, like the word run, could be, for example, either a noun or a verb, depending on where it is in a word. So a part of speech tagger needs to have the sentences, needs to have the tokens within the sentences. It outputs a POS, a part of speech. But then, because we are training, we also need to tell it, okay, where is the part of speech column, which is tags, kind of where is the label. And then you can also set the number of iterations if you want to configure the training, right? So, number of epochs, learning rate, and so forth. You create a pipeline, and then it's pipeline.fit. Okay. Once you have a pipeline, one important thing to know: pipelines are serializable. Okay. So if you want to reproduce the training, you can just serialize the whole thing. And that's one thing. The other thing that's obvious by design here, but it's important to note, is that you use the same pipeline for training and for inference. Right, and that's important because if you do inference here, of course, it's critical that you use the exact same sentence detector, right? The exact same tokenizer, right? So, for example, you remove stop words, you have to remove the stop words when you do inference as well. And having the code done the same way makes it much easier, right? You can train, then you can serialize the whole thing. When you load it for inference, you know that you're using the exact same configuration, models, and versions. This example shows you how to train your own name entity recognizer, which is really exactly the same thing. If you look at the code on the right, we import libraries, we start Spark NLP, in this case, with GPU, because if we use BERT embedding, GPU would actually help us. We have a core NLL helper functions, which reads a training data set for name entity recognition into memory. We use, and here, if you look at it, BERT equals BERT embedding.pretrain. So we use transfer learning. We use pre-trained BERT embeddings, right? We say, okay, we're going to calculate the embeddings on the training data. Then what we train is the actual name entity recognized, right? So NRDL equals NRDL approach, and then we configure it. Okay, so the source is which document, what is the token, what are the BERT embeddings of the token. We have where the labels are, right? So this is kind of the label that we train against. The output column is where we want the predicted result to go. And then we set things like, max epochs, learning rate, batch size, validation split. And very important, the evaluation log extended, which is true. So you have different options about basically how verbose you want the system to be in terms of what it reports back to you, so that you know how you're doing in terms of epochs, right, and learning curves, and so on. But once you're done, it's very simple. Anyhow, model equals pipeline.fit, training data, and you get your model back. Okay, on the model, you just do a dot transform on the data set, and that's your inference. Same code, local in a cluster, same code, CPU and GPU, same pipeline, training and inference. Okay, and obviously trivial to change the kind of embeddings you want to use. These are some examples for really the same code that you saw in the previous slide. Some of the results you get, right? So on the top you can see really comes the accuracy per label, which is more of a final result, and below you can see also the per epoch. You can also get basically more detailed logging, and then you can output that if you want to MLflow, to other tools to track your experiments and see how well you're doing. One important thing in terms of speed, to run this training on basically on a laptop. No, I'm sorry. This example you actually want to do on Google Colab. So this is on Google Colab, 16 GB with the GPU. Okay, so this is something you can do on your own Gmail account right now. On the entire Core NLL 2003 training data sets, it only took 16 minutes. Okay, so these things do not generally require large clusters to do, right? They do not require days and months. This is not like calculating GPT-3. Those kinds of things really you should be able to do on Colab. You should be able to do on your own machine. If you have 32 GB, it's great. If you have 16, you're probably good as well. Okay, just one more example here. You can also train your own document classifier. So this is an example of how you train your own multi-class classifier, right? So in this example, really you probably can understand the code on the right already. But basically what you do, you have a training data set that has two columns. It's a CSV with two columns. One is description, which has the news item, and another one is called category, and it is really how do we categorize these news items, right? So is it sports or technology or business or politics and or weather? And all you do is you start Spark NLP with the GPU. As a one line, you read the training data set, right, which is, as you see, just a CSV with two columns into a data frame, and you set up your pipeline, which is its document assembler. So take the text, create the document from it, calculate. In this case, we use universal sentence embeddings. So we load them, we load the pre-trained ones, and we use them to calculate sentence embeddings, and then we train our document classifier. Okay, so you set up the pipeline, you call .fit, and you're good to go. At this point, I'd like to show a few more examples of some other things that you can do with Spark NLP before we summarize. We are back at the Spark NLP in action at the demos tab here. And if you go to infer meaning and intent, there's some other interesting newer tasks that Spark NLP can do, which really I want to show because having more than 1,400 models and different tasks, there's a lot here that we never get to cover. So one thing I would recommend really just come and explore. And if there is a text mining task and you're not sure if we do it, you can just come ask on Slack or see if you can find it here. So one example, and also this is an out-of-the-box model, is text summarization, which we do with T5. So it's really it's a very close to state of the art right now, at least on English. We also have multilingual models that can do this fairly well. So you can see here, this is one example of a text. And basically, we just really, without any parameterization, we can summarize it. This looks at the Wikipedia entry for calculus and summarize it much more heavily. You can configure, by the way, within the model, how much do you want to summarize, basically? Right? Kind of, do you want a more aggressive or less aggressive summarization? This is an example on the Mona Lisa. So we have Mona Lisa, it's a half-line portrait painting, and we can see the summary here, right? And really, if you want it to be 30 words or 50 words or 100 words, you can do that. Of course, if you want to do it in Python, that's there as well. Another interesting thing is to be able to infer word meanings from context. So NLP used to be focused a lot on linguistic. Now it's really focused a lot on meaning. So what this can do is look at two sentences, look at the word, and tell you whether that word means the same thing in both sentences. So, for example, the expanded window will give us more time to catch the thieves, or you have a 2-hour window of timing in your homework. So the word window, you say, okay, does it mean the same thing? And here the model says yes. I think it does, which it does, because we're looking at a window of time. But for example, here let's look at two other sentences. It started to snow versus John Snow was an English physician. We're looking at the word snow, and the model will correctly tell us, no, the word snow means two different things within those two sentences. So this is very important if you're building semantic search applications, or really any search application where you want to understand, okay, if I'm just doing a keyword search and getting lots of junk, how do I know that things are actually relevant? Another very useful thing that you can do out of the box is find the semantic similarity between two sentences. Okay, so for example, look at these two sentences. Sign up for a mailing list to get free offers and updates about the product, versus subscribe to notification to receive information about discounts and new offerings. So here the model tells us, look, these sentences are 66% similar, right? Can consider very similar. Although if you look at the text itself, the only word that these two sentences share is the word about. Okay, but this model knows through the uses embeddings and other tricks that semantically these are very similar things. This is very useful. First of all, if you're doing things like spam detection, but also, for example, if you're building a customer service application and you get an email from a customer, and you want to find, for example, what's the most similar support article or knowledge-based article that we have to answer this question, right? Then these are the kind of things that are used today to implement those kind of use cases, right? Or finding most similar product, most similar article to this, right, and so on. I hope I only remember these words from the song. Can you give me the rest of the song? So let's say overall, there are quite a few other use cases here. There's automatic question answering, both open and closed question answering that are done. There are models here around translation. So there's language detection. There's also translation in more than 192 languages. And the last thing I want to cover, there's also a lot of work that we've done around healthcare. So we can recognize different types of clinical entities, specialized entities, different types of biomedical entities, relation extraction, entity normalization, and a lot of work around OCR, optical character recognition, especially on very noisy and low quality images. So I'd like to talk a bit about that to conclude. So Johnson Lab has two commercial software libraries that are licensed on top of Spark NLP. One of them is Spark NLP for healthcare, which provides state-of-the-art production-grade implementations specific for clinical and biomedical NLP. So there are separate implementations for clinical entity recognition, also it's a different code base. Also add things like clinical entity linking entities to ontologies, assertion status detection, so telling between patient is diabetic, patient is not diabetic, patient shows symptoms of diabetes, so patient's mother was diabetic, as well as relation extraction, so finding relationships between different entities, right? So did this happen before or after this event, or am I taking this medication to treat this symptom, or am I taking this medication, or has this symptom started after I taken the medications? There are over 30 different types of relationships that are available out of the box. So if you're interested in clinical or biomedical NLP, definitely try it out. There's a free trial and see if it works for your own use case, because this really provides the state-of-the-art accuracy as well as bit of scalability to that industry. And the other licensed library is Spark OCR, which actually, unlike what the name suggests, goes beyond optical character recognition to really do automated understanding of visual documents. So it will automatically read and extract structured data, tables, or just do information extraction from PDF, whether digital or scanned, for images and for medical imagery, so DICOM images, pathology images and other formats. It also has the pipeline model, which is very useful because it has, you can see on the transform part of the slide, a set of image enhancement filters, which enhance accuracy, especially if you're dealing with things like old faxes, photographs that someone took with a mobile phone, and you have things like shading, hiding, imagery, natural things, faded images, folded paper, and stains. Some of the things you can see in the examples here. So especially if you need to extract information for low quality images or documents, that may be able to help you. So those are just some things to consider. But really, if you want to start, definitely start with the open source library. See if if you like the API, how fast it performs for you, how well it works for your use case. And other than that, there are tons of other online resources. We saw there are over 100 demos and notebooks, which I just showed you online. But they're also under the Learning Hub. There are tons of case studies, especially with the focus on industry case studies. So beyond kind of the nuances of how you train specific models, there are a lot of lessons learned on how you actually put those systems in real production cases, scale them, deal with privacy, compliance, responsible AI issues, which I would highly recommend that you start from if you're really trying to put a real system in use using this kind of technology. So at that point, thank you. Thank you for listening. You have here the two main links to the live demos and notebooks page and to the getting started page. Other than that, I'm always happy to listen and learn from what people are doing and trying to do. So please feel free to reach out to me if there's a need. Thank you.